In this video, I'll show you how to use Castep to get publishable results for pharmaceutical type compounds without the need for Material Studio. The parameters we're using for the calculations are based on this paper. Now, if you want to read this description of the co-crystals and salts, pause the video. The ETH-SAL system is the one we're going to look at. This is the paper in which we published the results. The link to it is available on open access, is in the description of this video. The ETH-SAL system can be a co-crystal or a salt depending on whether the proton is on oxygen or nitrogen. We start by finding the CIF file for ETH-SAL salt form. When we open the CIF file, USCL converts it to ShellX files. We can use the ShellX file to look at the structure by clicking the Ortex toolbar button, and in atom mode, when we look at it, we'll see that the sulfur's actually disordered in the structure. Now, this won't do at all for the calculations we want to do. We're going to have to remove part of the disorder. The nitrogen is protonated, and the proton has come from the carboxylic acid down here, and this is why this compound is a salt. Now, we have to remove the minor component of the disorder. We can easily do this by editing the ShellX file. Edit the INS file, and the two sulfur positions are shown here, S1A and S1B. We need to disable the minor component. Now, the site occupancy of the major component is 85% of the time, and we're going to remove the 15%. You do this by putting 4 spaces in front of the name. That effectively removes the atom from the calculations. Now, for cosmetic reasons, we're raising the site occupancy of the only remaining sulfur to 1 by putting 11 into the ShellX file. Now, when we look at the structure with Ortex again and switch on the terminal ellipsoids, we see that there's only 1 sulfur. So we can go ahead now. If we go to the lattice pack dialog using the toolbar button and calculate the lattice pack, we check Castep files and press OK, and the files have been generated. We can exit Ortex now. We need to find 6 files. They come in different varieties. There are cell files and parameter files and 2 other files. Now, we can see the 2 cell files there. There's an F version and an M version. These are for fine and medium resolution. Fine resolution is needed for publication. So we've got to find the parameter files that are up at the top of the folder. So select those 2. And we need POSCAR and Precalc as well. Copy these 6 files and put them into the folder where we're going to do the calculations. Now, the folder, as I described in another video, is C, Castep, Castep version, examples, and finally the name of the job, which is ETH-SAL SA in this case. So we need to go to that folder by starting the Linux or Ubuntu and type cd/mnt/c/cas lowercase, press tab, and it finds the rest of it. cd cas uppercase tab, cd ex cd ETH-SAL SA will take us to the folder where the files are. Now, we need to get K points first of all. Notice the K and P are in uppercase. This generates a K points file. We can see it here on the left, and if we edit the K points file with Notepad, we just need the fractional coordinates of the K points. Copy those to the clipboard and edit the cell file for fine resolution. Edit the F cell file. Now we can paste the K points into the K points block at the top of the file, and we need to change the VASP format that we have here to Castep format. The probabilities must add to 1. They currently add to 8. If you divide 2 by 8, you get 0.25, so we need 0.25 for each of the probabilities, which the 4 of them will then add to 1. Now we don't need the rest of the line, so we remove that. Save the file, and we're now ready to run Castep. Now to run Castep, you type the command castep.mpi space job name, and the job name is ethsal SA _F for the fine resolution version. It's now running, and if we look at the left, we can see new files are generated. The first files that are generated are the pseudopotential files. There's one for each atom type, and the calculation runs on. Now, to get a view of the calculation in the File Explorer, press the path and type cmd return to open a DOS box in that folder. Then type ucastep job name. This will run a program which gives you a brief synopsis of what's in the output. The file is pptest.cao. If you open that with Notepad, we notice that it's saying last fractional coordinates there at the top, and if we pull it down, we'll see that the job's been running for a while, and it's run 27 iteration cycles, and it's not quite finished. It's almost finished, but not quite. You can put on Task Manager to see how the CPU time is being used up, and you can see that it's going up and down as the calculations are proceeding. Now the calculation has finished after some considerable time, of course. If we press up arrow, we get ucastep again, run, and a new version of the synopsis file. And we can see we now have refined fractional coordinates, so the job is finished. And if we go to the bottom, we can see yes, yes, yes in the last 3 lines there. And this is the enthalpy we need for our publication. Now in the paper we have a table of delta E, which is the difference in energy between the co-crystal and salt forms for each of 5 different series of compounds, and in every case the correct, more stable form is predicted.